In the last video, we set up things so that we could move an object around with blueprints and make it bounce between 2 points. And we created a function in blueprints, but we want to be able to do this in C++ so we can understand the connection between the game engine and C++ and blueprints. Fortunately, the game engines allow you to extend the game engine through C++ and extend blueprints with new nodes and new properties for your objects so that you could then put them into your level and create things pretty easily. In order to do this, we're just going to go ahead and create a new scene as we've done before. So I'm just going to go to File and I'm going to say New Level, and I'm going to click the default one. And then I'm going to quickly save it so I put it in the right location. So I'm going to put this one under Videos here, and I'm just going to call this Lab 2, since this is sort of like what you want to do in Lab 2. So we have our level now, and now we want to create a new C++ class that's an actor. And in order to do that, we right-click over here on New C++ class, and we're going to extend actor. Okay, so we inherit from actor. You could inherit from pawn, and for your game, you most likely want to do this because pawn will allow you to more easily connect input to your objects. So it has some default behaviors that make it a little bit easier. But if you start with actor, you need to sort of build things up from scratch, which is what we're going to do here so you can see how it works. I'm just going to leave it my actor because that's a fine name for it. And I'm going to give it a directory I'm going to call Videos Lab 2. And I will say create class. Now we wait for a minute while it recompiles. Now what it's doing is it is compiling C++ code and extending the editor. So it's sort of doing it's going to do what we call a hot load of the source code into the editor, so that the editor now has access to the same objects that we're creating with C++. So it's actually a pretty advanced and kind of interesting but complicated system. All right. So what you saw is up down here, we saw these things pop up saying, hot load complete. It also popped up my windows. Now, this is an unfortunate thing on Macs that Macs like to do. When it opens the windows, it just opens the individual windows, and we actually want all of Xcode to open. So I'm just going to come over here and do two things. First, I want to double check to make sure that my classes were added properly. So I see my actor here. And then I'm going to come over here and I'm just going to say refresh Xcode project. You might need to do this if you've downloaded your Git repository and haven't downloaded a fresh copy to make sure that it was working, because our git ignore is going to sort of remove all the project files because you don't need to really upload those, but we can just regenerate them at any time by clicking refresh Xcode project. If you're on Windows, obviously this is refresh Visual Studio, or if you're using CLine, then that's another example of one that would be up there. So it's just going to refresh the project settings, and then I'm also going to come back over here once this is done, and I'm going to say open Xcode, so that the whole project will open instead of just an individual source editor window. You'll notice that you have two things here, and this is kind of useful, and you'll see this in C++, in Visual Studio 2. This actually lets you see the source code, in essence the headers and stuff like that are connected to UE4. And so if you ever want to look something up or look at the source code, you can do that through here. Most of the stuff that we deal with is in runtime, and there's obviously a lot of things here. It's sort of worth exploring, and it's also the reason that when you're on a Mac, you'll see this indexing take forever because it's trying to index all these files. On our project, this should be named the name of your project for Unreal, and our source code is where things are going to live. So you'll see that I have different locations here. Now I put my videos under labs, which I didn't mean to do, but we're just going to leave it for now because it doesn't really matter. But what we'll really see here, the most important part, is that we'll see these two classes that get created. So it creates there's a template that's used to create these objects, and don't mess with the code generally. In particular, U class has to stay here. These includes you don't need to change. They've set up the includes a lot better than they used to be, so really all you ever need to do, for the most part, is just include your actor, and then this is going to include sort of the minimum set of objects that you need for your class. So it's pretty nice. So now we want to extend this class to sort of give us the behavior that we want. And we'll see a couple of methods that should look familiar. If you remember in Unity, when you did that, there was a start method. That's the same thing as begin play. Then there's a tick method here, and that is the same thing as update in Unreal. The difference is that here we have a constructor, and unlike Unity, we can write our own constructors and we have to do certain things. It gives us sort of the initial boilerplate for doing that. So by default, we have to set, primary actor tick can never tick to be true. And the reason we do that is because this will allow your class to actually receive these tick calls. If you don't have this set to true, then your object's just not going to receive them. And it could be useful for like efficiency reasons, like maybe you're inheriting from actor, but you don't need it to tick, or you're going to update it from some other, location, so you don't need its own tick to be called. And so you might set that to false occasionally. So let's look at setting up some things that we can expose to the blueprints, to our blueprints and to our editor. And the first thing we want to do is, we want this object to move up and down like we had in the blueprint. And so under public here, I'm going to declare a U property. So U property tells us that it's going to be like a field that we can edit. And we have to give it some rules here. So edit anywhere, for example, and blueprint read write. And this is enough to let it access the property inside the editor and inside of blueprints. If you were to leave one of these out, for example, you might not see that. So I'm going to put speed here. And you notice that there's no semicolon here. This is what we call a macro in C. It's like a lame form of a racket macro, but it does code replacement. So it's basically putting some boilerplate code before your a declaration of this variable in order to make all of this work. So it looks sort of magical, and it doesn't look like C++ because it's not. It's just a C++ macro that's doing some expansion to figure out like how to declare these things properly. Because a lot of this stuff ends up being boilerplate, so they're trying to keep you from having to write all of that. So in addition to speed, we probably want an end position. So we'll say U property edit anywhere, blueprint read write. Now that I think about it, I don't remember if I can just leave edit anywhere. I'm going to delete this just to see if we can. So when we get there, we'll know if it's accessible. In Unreal, our three-dimensional vectors, in Unity you mostly used, you use three-dimensional vectors all the time, even though we were doing 2D games. Here, we're going to use F vector for anything that's like a three-dimensional point. All right, so this is going to be end position. And then we're going to do another U property. We don't want this one to be editable, so we'll say visible anywhere. And we're going to call this the initial position. So in essence, wherever this object is placed in the level, we're going to grab that, and we want to store it so that we can sort of bounce back to it from whatever new location we're at. Finally, we want to know what our target is, so what point we're moving towards, and it's useful to be able to see this live in the editor. So again, what we want to do is make this visible anywhere. We don't really need to edit it ourselves, though you could, but there's no reason you would do it, like on the fly. So, except for like debugging purposes. So we'll call that target. So this gives us the properties that we kind of need to set things up. Now, right now, because it's an actor, it doesn't really have any components on it. And in particular, what it needs is a scene component. So the scene component will contain the transform to let it be drawn in our scene. Now, that's just going to be the transform. What we also need on top of the scene component is some way to represent the object in three-dimensional space. And in order to do that, we're going to use a mesh, okay? And we'll be able to set up a mesh through code. And so we're also going to make this a U property, and we'll say visible anywhere. And we will say U static mesh component. And the star, if you remember, is a pointer. So we're saying that this is going to be a pointer, and we'll just call this the mesh. It will show up in the editor like that. finally, if you remember in our blueprints, one of the things that we did is we created a function that would let us move towards from one position to another. So all of these properties, all of these things are going to make up properties that we can edit, but we also want to create new blueprint nodes. We'll come back to that actually once we get to that point. So let's go ahead and look at how we create the actor and sort of make sure things work initially. So here's my actor, and you'll see that I have these default values. I want to point something out. Because we're inheriting from actor, and actor inherits from UObject, we automatically get this base class that's called super, and in essence it's a way that their object system lets us access our parents. And I think part of this is because a lot of this was built before they were fully using C++ and blueprints, and they were basically building their own scripting and garbage collection system on top of C++ to make the programming easier. So super is just another way to access your parent. You know that in C++ you could in theory just do this, for example, and that would access your logical parent. But the super needs to be used because they have their own sort of hierarchy. So whenever you want to call your parent, you do that. The reason that we do this first is that, we want to make sure that any construction that may have happened from something that we inherited actually occurs. So now that we have that, we want to go ahead and take a look at the code for constructing this actor. And I'm going to go over to the constructor first. The first thing I want to do is initialize my speed, and let's initialize it to something like 100, for example. If this is unfamiliar to you, this is a way that you can initialize the variables in your class. And these things get initialized before the body of your constructor is executed. But it's just sort of a clean way to show which variables you're initializing. And also, if you need to initialize an object, you can pass, you can pass arguments to its constructor by putting them up here. Versus down here, it's just a little bit messier, and sometimes it doesn't work the way you want. So sometimes you actually have to use this this colon operator here. So we have let's set up our mesh first. So if you remember, we had something called the mesh. And in order to construct it, we are going to use something called create default sub object. If I can type. One thing you'll notice is that I'm not getting code completion, and that's because I still haven't finished indexing this thing. And so it'll take a while before code completion starts ramping up on this system. So create default sub object, and it's a templated method. So I want to say u static mesh component, and then what I need to pass to it is the name of the default subobject of the object I'm creating, and I'm going to put mesh in here. Okay, and this text here is a Unreal type of string, so again they also have their own string version, and the string their string has its own like garbage collection and methods on it, and they have different kinds of strings depending on what you're using them for. But we have to pass this text here to give it the right type of string to get passed to our templated function. So that will create the default sub-object, and if it's a C++ class, so basically anything that's a C++ class needs to use create default sub-object. And there's some other methods that you can use, but basically if it's a C++ class, you need to use that. And now we need to set this up. So we're going to say the mesh, and what I mean is we have to attach it to our root. So we're going to say set up attachment. I think I got some code completion. That was nice. Root component. So the mesh setup attachment root component, this tells it to make it, in essence, to attach this mesh to the root component. And the first component that is attached to the root component becomes, in essence, the root component. Since this is the first one and we're on an actor, our mesh is now the root component. So anything we do to the actor is going to generally affect that root component first. So for everything else that's an asset, we have to use, it is called f object finder. Okay, And what this does is it's going to look in the assets folder and figure out how it needs to load that particular asset. So the difference here is that, assets are things that we can change on the fly and the game engine can load dynamically. With C++, so things that are classes, these are static objects. C++ is a static language, so everything has to be compiled before you sort of put everything together. I mean, you can use dynamic libraries, but even those that linking, like it's going to verify that all of the expressed methods are defined properly and things like that. So here, if it's an asset, so things like meshes or things like textures or whatever, we end up using another method for that. And so we're going to define this as a static variable. So we'll say static constructor helpers f object finder, and you see it's code completing for me very nicely. And I'm going to say u static mesh. So we know that the kind that it's returning is a static mesh. And this needs to have a name. Okay, so we're going to call this cube, how about cone visual asset? And again, we have to use our text here. And the location of this is going to be based off of something that it begins with a /. So this is, folder notation, directory notation. And there's in essence, Unreal creates a virtual directory. And it always begins with /game. Anything that's below /game is in your content folder. So in essence, you can imagine replacing this with the word content and it would be the same thing. So starter content. So I'm going to try to load from starter content shapes and then shape cone. I don't like the indenting it did, so I indented it more. So this, remember, this is all one declaration. This here is in essence like the type, and this is the name of the asset. It's a little bit weird, but what it's going to construct is a special kind of object. It's like some kind of asset object that we can then check to see if this was loaded properly with. So this is, again, just to be clear, this is the type. The reason that we make it static is because if we're creating like millions of these, a static variable in a function in C++ is only ever allocated once. So the first time this is allocated and created, it's not going to get called every time we call a new constructor, for a new instance of my actor. It will only get called once, and so we do this for efficiency reasons. So once we have this, what we really need to do is check to see if it's valid. So we'll say cube visual, it's cone now, cone visual asset succeeded. So we need to make sure that it actually loaded. Then we can say the mesh set static mesh. And we're going to use cone visual asset object. All right, so this object retrieves the actual type, this uStatic mesh, out of our little asset object. And you should only try to retrieve it and assume that it's correct if you're checking succeeded. And then what we need to do at that point is say the mesh set relative location. We're just mainly doing this so that we, when we get more into the 3D math, we'll see that every object has its own 3D space associated with it, and so we want to make sure that this is loaded basically at the origin of that 3D space. So 0, 0, 0, 0, 0, 0. And now we've set its location. We want to probably put a material on this, and the materials are things that will allow us to correctly put texture or put an image, in essence, pasted onto the mesh. So the mesh is really made up of triangles and three-dimensional space, and then the graphics card draws those. And the material determines the properties and the lighting of how that works and what you actually see. So we're going to create a material in order to do that. So we'll say static, again, constructor helpers. and then we'll say F object finder again, and this type is going to be U material interface. They use an interface for these so that different kinds of materials can be created, and we're going to call this cone material. And this material is also something that you will find in your starter content. If you didn't load your starter content, you probably want to add it to your project because there's a lot of stuff there. So starter content, materials, and the name of this is M cobblestone pebble. We're just going to put a random image on there. Texture so it looks a little more interesting than a white cone. All right, so that creates that constructor helper. And again, we need to do the same thing. If cone material succeeded, if I can type here, then the mesh set material. Your objects can have more than one material. We want this to be the first material, so we're going to use 0 since we, of course, we count by 0. Material object. And that will be enough to create the material. So I'm just going to put a couple of notes here so I remember what I'm doing. And you should do this too. Please comment your code. Create the material to put on the cone. And then here we create a static mesh for a cone. All right, at this point, if I were to go ahead and compile this, then this cone, we could drop it in here. So let's go ahead and do that. There are two ways to compile it. One is from your system, from Unreal here to compile it. Now I'm in Xcode, and so I can just hit Command B and it will start trying to compile it. Hopefully I don't have any errors. This error was from a previous thing, so I'm hoping that will go away. And so it's going to run the build tool. It's not that exciting because I can't sort of see what's going on. So I'm going to come over here and just sort of wait for it and see if I can see it getting compiled here. It may depend on which thing is being built here. Well, it says it failed. So let's go find out why it failed. And I'm going to just compile it here so we can just sort of see what's happening. Whenever you compile from here, you will definitely see this. It might be that the wrong target has been set up here, and so I will set up the target if that's the case. So we're compiling. If we want to see what's happening, we can show the log. It did definitely fail. And it said, oh, it's because I named it cube material instead of cone material. Oh, yes, now, Xcode has woken up. So this should be cone material, because obviously cube material didn't exist. All right, let me check my labs, my Mac. Oh, that looks right. So I'm going to go ahead and rebuild it again and take a look. You can look over here in Xcode at sort of what the build status is, and then you'll see issues when they pop up for those of you using Xcode. In Visual Studio, you usually have a console that pops up automatically. They, for whatever reason, like to hide a lot of that stuff for the Xcode developers. And I can take my message log. Actually, this is pretty useful to have out, so I'm going to put my message log down here with my editor. Whoops, I keep dragging it to the wrong place. There we go. Let's move it over a little bit. Put my out. Well, maybe. There we go. All right. So in theory, this has been built correctly, but I don't see it updating. So that's a little bit odd. If you don't see it updating, like this actor should already be reflecting some of what's going on. I'm going to hit compile again here just to make sure it's compiling to my editor. What happens is that Xcode has a bunch of different targets, and you actually have to sort of reconstruct the editor every time you add new C++ classes. So it is compiled, but I don't see it. I'm going to go ahead and drag this in here. Oh, now it's showing me very nicely. You'll notice that this is a cone. You'll notice that it has a pebble material on it. And then this, in theory, will get updated to eventually be, to look correct. And so we'll see sort of the right thing when we do it. And I can already hit play and look around, and I can say, like, oh, look, there's my cone. Looks like it's a cone made out of pebbles. All right. that's a good start for now. So after this, what we're going to do is add some behavior to this object. Now let's go back to the editor so we can add some code to blueprints. Oh, I wanted to show you one more thing really quick. Since I've added this object here, it's just called my actor, but what you'll notice now is that under my actor, we'll see these values that we expose. So the speed, the end position, the initial position, and the target. And in addition, right, we see that we have a static mesh that's defined, it's shaped comb. This is because we set up all of those values earlier. This starting position is where it started at. Initial position is nothing's been really set for that, and the target, nothing's been set. But the speed is 100, which is what we wanted. Now let's go back and fix the rest of this. If you recall, I said that we were going to come back and add a function, and what we want to do is add a kind of function that's going to be exposed to the blueprints so we can use it in a node if we would like to. We're going to call this move towards, and in order to do that, we will use uFunction. So uFunction is going to be blueprint pure, meaning that it only needs the inputs and the outputs in order to execute. It's not doing, in essence, like a state change. And so I'm going to say static f vector. That's going to be the return type. If you remember our move towards, we did the same thing in blueprints. It returned the vector of the next position we wanted to be at. And it takes 3 arguments. Now these 3 arguments we specify by using something called uParam. And uParam lets us customize the way these things look. So display name. This will be what is displayed on the node in blueprints. So we'll use the word current location as the display name. And then this type is going to be f vector. And we will call this current location. Then uParam display name equals destination. And the type is f vector. And the variable name will be called destination. Then uParam, if I can spell it correctly, display name equals max distance delta. And this will be a float, and we will just call this max distance delta. So these are the parameters to my function. There are 3 of them. I'm going to move this down because, again, it doesn't look great. And let's put it about right there. Because then I can just really quickly, if I look at my source code, I can see what these functions do. I'm also going to put a comment here. And this comment is going to say, given a current location and destination, and a max distance to travel, this function will return either the next position by moving the max distance along the vector from the current location to the destination, or the destination if we would pass up the destination. In other words, we don't want to pass up our endpoint, we want to end exactly at our endpoint. So that's what the function is going to do. Now I need to define it here. You'll notice that I had to make it static. This is just a requirement for blueprints because it can figure out more information about this. But also there's not this pesky this pointer that's passed to it. So it sort of keeps you from doing bad things, especially with blueprints. Or if blueprints have a problem, they don't have access to your this pointer. So that's generally a good thing. So let's define that move towards function. Remember, it returns an f vector, and this class is called myActor, and then this is called move towards. And the types it takes are an f vector. Notice that we don't have to put the u params here. So current location, f vector, destination, and float, max distance delta. Now, what do we need to do? Well, we're going to do the same thing we did in the other lab. We're just going to figure out the vector that points in the direction of the destination. And in order to do that, we just simply say destination minus current location. We also need to figure out the distance to the destination so that we can compare it with our max distance delta. Now, here's something that's interesting about games is that we're trying to draw 60 frames per second and do basically millions of calculations in order to make everything draw very nice and pretty for the end user. So we try to save, speed in obvious places as much as we can. So we're going to do that here. And whenever you calculate the distance of a vector, so in essence the length of the vector, if we were to try to calculate the length of towards, that would require a square root operation. Well, it turns out that square root operations are pretty expensive to do compared to a multiplication. On most of your CPUs and GPUs, a multiplication can happen nowadays in a cycle. It used to take more, but it's such a common operation that it's been optimized. Whereas square roots can actually take hundreds of cycles because it's trying to figure out, a precise square root. So we don't really care about that. If you think about the Pythagorean theorem, right? So what does it tell you? It tells you a squared plus b squared equals c squared. That's where the square root comes into play, right? Because we're trying to find c, which is the distance between the 2 points, and we have to take the square root of a squared plus b squared. What that means is that most game engines will have a version of length that includes the square distance because it's faster to compare the square distance. We're going to do that. We're going to use that function. So we're going to compare the square distance. And in order to do that, we will say float square distance equals towards size squared. We will also then figure out what the max squared is, and we will simply just say max distance delta times max distance delta. Now, we could get really clever and say something like that, and that would left shift it too much if we just had values that weren't floating point numbers. See, that's the problem here. These are not floating point numbers. I mean, these are floating point numbers. They're not integers. So don't try to be clever and do weird things like that. You could sort of force it with C. Please don't do that. Again, multiplications are fast, so let's just stick with this. All right, now let's do a simple comparison. Now you might be asking, but I had to do this multiplication every time. Well, yes, it's true, but it's faster than finding the actual size of this by taking the square root of this. So that's why we sacrifice a little bit of time to do the multiplication. So finally, we can now do some comparison. So if squared distance is less than squared max, that means that we are too close to the point, and so our end point should be that final position. So we're just going to simply return destination. And if we don't do that, the thing is that what we really need to do now is normalize this towards vector. We're not going to normalize initially because we don't know if we're going to even need to use that, but we'll normalize only when we need to. So we can now say towards normalize. And this, if you recall, gives you a unit vector. So the length of this vector, so the distance is 1. And then we can now say return current location plus towards times max distance delta. Now this scales, this max distance delta is going to make this towards vector be the exact length by scaling it, because the towards length is guaranteed to be 1 now. So it will end up being the correct length that we need to move. We add that to our current location, And then this gives us the next position that we want to be in. Now we have move towards, and we now want to put some logic inside of our tick function so we know what we want to do every tick. So the first thing is, if we've reached the target, then we're going to switch the target so we can start moving towards the new point. So we do that by simply saying if get actor location equals target. One thing to remember is that if you look at f vector and you look at this equals function, what you'll find is that it will also use a like a delta to figure out if you're within a certain distance, it's going to return true. So it's not a precise equals, because again, with floating point, we can't be guaranteed that we'll precisely equal a value, but instead it's more like a nearly equals by a really, really close amount. So if that's the truth, then we're going to say target equals, then if target equals, end position, we basically want to flip-flop here. So I'm just putting some logic in to do that. Then we'll say target is going to be equal to initial position, else target equals end position. So that will give us the flip-flopping between positions. And now what we want to figure out is what our next position is. So f vector next position is equal to my actor move towards, and then we're gonna pass our get actor location, the target, and then speed times times delta time. Where did delta time come from? That is simply the parameter that's passed to here. In Unity, you would have put time dot like delta time or whatever. Here, it gets passed into our function. So we need to multiply our speed by that so that we're frame independent if we don't do that. And now we can just say set actor location to be next position. And then we're done. We can compile this, and in theory, this will work if we haven't missed anything. But we have. Wait, I just noticed. We don't have anything in begin play. We need to set our initial position. So how about initial position is equal to get actor location. That way we set it to wherever the level builder had put it. It will be there. And then we'll say target equal end position. So whatever the end position is going to be set to is what we're going to fire off towards. Now, of course, this end position has to be set, when the game is running or before the game is running, so that this gets initialized when this actor is built. So let's go ahead now that we've built that, we want to go ahead and do a quick compile here. And then we should see that we have the values in this actor show up here in my actor. In fact, I'm going to back up a little bit from this object. I'm going to move it so it's not on 0, 0, 0. And we should see initial position get set to whatever its position is. Its position is now -90. And once we save this and then we run, we can come over here and click on my actor and take a look. Now we're switching between a couple of positions, it looks like. So where are we that we're missing this? Ah, yes, there we are. Beautiful. If you get into the window here because you were moving around, you can hit Shift F1 and it'll give you the mouse control back. It's a little tip that you might want to use. We can change our end position to whatever we want. So we could, for example, move it upwards in the air. And then now it will go upwards. We can also increase our speed if we wanted to. 200, move it twice as fast. 20,000, to go really, really fast. So, the speed is basically launching it so far that it's going between the end and the start point. I apologize. I should have given a flickering warning before doing that. So let's go ahead and try to fix that really quick. But what we do see is that we now, move at a reasonable speed as needed. So here's a very slow speed. Hopefully calm you down. So that's it with moving and setting up some, your actor, setting up your material, setting up your initial component with your mesh, and, the C++ stuff. The main issues that you're going to run into generally are that you have some problem and you have a bug in your code and it won't compile. And if you then close your editor and it tries to rebuild your lab, you're going to run into problems. So if that happens to you, what you want to do is go in and comment out the code that had the error in it so that you can then rebuild your editor. Because if your editor fails to build, you just won't be able to launch anything. And that's probably the biggest hassle that we see when we're dealing with Unreal and C++. Otherwise, they've made the code fairly clean in terms of, how do you extend things. It does require that C++ so that all of this makes sense, that this is a dereference because this was a pointer. And we know it was a pointer, right? Because we declared it as a pointer with a little pointer thing here. It's also good to see how we create functions. These functions will show up. Oh, I should show you that really quick before we go here, which is simply that now that I have this object, I can go create a blueprint for it. And let's go ahead and put this into, how about videos lab 2? And we'll just call it my blueprint. I'm going to drag this and put it up here. And if I look at the event graph, we'll see now that we have a new function called move towards. And it looks like that. And this was defined. You can see that the comment is the comment that we put in our code, so it's a good reason to comment. And it gives me, the inputs that are vectors and the output that's a vector, and then a max distance delta. You can actually put a U pram, by the way, that will rename this to be like next position, so it's obvious. But we didn't do that. But, feel free to look at the code to do it. So, these things are now accessible also inside blueprints once you declare them inside your code as U functions. The difference between Blueprint Pure and other kinds is that in order, this is sort of a one-way communication. But if you wanted things to, like in essence, call blueprints from your C++ code, you can create a special U function that is a kind of event. And in essence, when that gets called, code will get executed. And those things will appear as these kinds of events here. And then you can drag and execute wire off them and make things happen. So if you're trying to think about, like, how do I connect my C++ code to my blueprint code, that's sort of how you do it. All right, thank you.